So, welcome back, and today in the study of fluids we will deal with what is known as the streamline flow and build up the case to learn about viscosity of fluids. So, streamline flow is the fluid in motion, and here we talk about a steady flow. In a steady flow, the velocity of each passing fluid particle remains constant in time. This does not mean that the velocity of different points in space is the same. It may be different. At another point, the particle may have a different velocity in magnitude or direction. Okay. But every other particle that passes the second point, for example, one point is another point. Second point behaves exactly as per the behavior of the previous particle. Okay. The same behavior is followed by each particle. And in doing so, each particle follows what we call a smooth path. Each particle follows a smooth path. Paths of different particles do not cross each other. Do not cross each other. I'll tell you the reason for that. So, we define streamline is a curve. A streamline is a curve. On that curve, the tangent at any point is in the direction of the fluid velocity. For example, I have shown here the tangent here, tangent here, tangent here, and tangent here. They show the direction of the fluid velocity. As I said before, no two streamlines can cross. Because, why? Because it shows the direction of the fluid flow at that point. And if two streamlines cross each other, that means that at the same point there are two velocities. Okay? And that is not possible. That is also the case in lines of field and lines of force, etc. in different disciplines. We'll see that a streamline is a continuum of lines, okay, and we'll talk about laminar flow. So, the typical trajectory of a streamline flow that was shown here, okay, it shows between the points P and Q. I have taken purposely a trajectory like that, and when this particle over here moves like this, you can see that at every point I have shown the velocity associated with the particle. Okay, particle of fluid. So, in fact, this is a typical trajectory of a fluid particle. So when close by lines, which are called streamlines, they come over each other, they may form even a tube like this. I have taken again an arrangement in which the liquid is flowing from P, entering P and exiting Q. Okay? In the steady flow of the map is stationary, okay, and a continuum of lines results, which may give us an idea of a tube of lines which never cross each other. In this arrangement, I have the points P, Q, and in between I have a point R. So naturally, the area of cross section over here, AR, is more than that at P, also at Q. Okay. So you can see that whatever mass is entering over here, the same mass is leaving over here and leaving over here. Okay. The same mass leaves here, here and here. In the same time interval, delta T, and delta T. Okay. So the mass is there. So AP, AR and AQ are the areas of cross section which are perpendicular to the lines of flow. They have been taken, and the resultant velocities we just take Vp, Vr and Vq. The time is the same and the mass flow is also the same. Okay. Now I can write about this is the density, this is the area of cross section, and this is the length Vp delta T. So that gives the volume. Okay. So rho A and rho into the volume. Okay. So mass is equal to the density into volume. Okay. Like rho is equal to mass upon volume. So I am writing the same thing for the point P, for the point R and the point Q respectively. This is rho R into the volume and this is rho Q into the volume. Okay. So these are, and delta M does not change. What flows are what fluxes out, okay, or fluxes in is the same. Now the liquid is considered to be incompressible. It is not compressed. So that the densities at the point PQR are the same. Okay. If so, then what we find is that delta T is the same, delta T. So if we equate these values, then what I get is that rho into delta T, rho into delta T, rho into delta T, they will cancel out, and what results here is AP into VP, that is the area of cross section multiplied by the velocity, area of cross section multiplied by the velocity, area of cross section multiplied by the velocity at point Q, P, Q, R, they are equal. So in general we can say that at any area of cross section anywhere that we take, okay, the value of A into V is a constant. Okay. So this is called A, V is equal to constant, is called the equation of continuity. Okay. And this is nothing but conservation of mass principle that we have taken. Okay. Or we have talked about the volume flux or the flow rate. Okay. The crux of the continuity equation for a streamline motion is that the area of cross section into the velocity, which is a measure of the mass transfer, or the mass flux, is a constant. Now we find that the area of cross section, the point P, is less than the area of cross section of point R, which naturally shows that the velocity at the point P must be greater than the velocity at the point R. Okay, that means in between there is a continuous deceleration of velocity. Okay, there is a retardation which takes place. The velocity becomes lesser and lesser because the area of cross section becomes larger and larger. Conversely, the AR value, or the area at point R, is greater than the area at point Q, and which gives that VR is less than VQ, which means that from R to Q the velocity keeps on increasing, so there is an acceleration. Okay. and this acceleration is positive, and this acceleration over here is negative. Okay, so you can say that there is negative and positive acceleration which occurs. Now, one of the features is that the steady flows occur at low flow speeds. Steady flow occurs at low flow speed. Speeds have a limit beyond which, and this limit is called the critical speed. Beyond the critical speed, the motion becomes turbulent. It is no more streamlined, no more steady. Okay. This happens when a fast stream with a velocity or a speed less than the critical speed, it encounters rocks, etc., which has been just shown over here in this diagram and this diagram. This is for a streamline and this is for the turbulent situation. Okay. In the streamline you can see that the velocities may be different in the different layers, different lamina which are there. In fact, you can see the difference, although it is not drawn to any scales, proper scales, but you can see that the lines, all these lines are parallel to each other, and the separation between the lines, separation between adjacent lines is more towards the edges of the pipe than in the center. And the more the separation, the slower the velocity. Okay. So this indicates that there is something called viscosity, which we will discuss shortly. Okay. But if to the flow of this we subject some kind of a rock kind or a plate kind of a thing, what happens is that these streamlines which are coming up to this point, okay, in a streamline, after they encounter this, they start going like this, and they also whirl, okay, so that we call that in the water, in the turbulent flow that is there is a foamy whirlpool, okay, foamy whirlpool or white water rapids are formed with some foam. So this is exactly what I was talking to you, wanted to introduce to you the kind of fluid flow, and in which we have the streamline flow and the turbulent flow that I have explained to you. Also, and doing so, I have told you about the very sound principle, and that is AV is equal to constant in a pipe in which there is a tubular flow of liquid. Okay, and this is called the equation of continuity. Okay, so next we learn a beautiful principle of the flow of fluids. That's called Bernoulli's principle. Bernoulli was a Swiss scientist, physicist, who lived during the years 1700 to 1782, and in 1738 he came out with the beautiful principle, Bernoulli's principle. In fact, Bernoulli's principle is an application of the conservation of energy principle. Okay. It relates the change in pressure between 2 points just a bit in a pipe of varying cross section area of cross section at varying heights to both velocity changes, delta kinetic energy, and elevation changes that we call delta potential energy. So the pressure, the kinetic energy, and the changes in the potential energy, they are related in the Bernoulli's theorem. Let us consider, to understand that principle, that we have a flow of liquid through a pipe, as I have shown there. Here the area of cross section is A1, which I have just shown to be continually increasing when it comes to this point D, and we consider it, the area of cross section is A2. The pressures at the two ends have been taken as P1 and P2, and the velocity over here at this point is taken as V1, and the velocity here is taken as V2, and that complies with the continuity equation that we have obtained. A into V is equal to constant. Okay. Now, the time delta t is very short, so that what I have shown over here from B to C, the flow of the liquid to in a length V1 delta t, and another at here from D to E in a length V2 delta t, this is apparently exaggerated. The delta t is taken as very small, and so this is a small change of mass which will take place over here, and the same small over here, so that we can consider that from B to C the area of cross section A1 remains unaltered, unchanged, and so does the velocity V1. Similarly, from D to E, the area of cross section remains the same, and the velocity also remains the same, because this delta t is very small. Okay. Now, as I told you, V1 delta t is a small distance BC of constant cross section A1, and V2 delta t is the small distance dE of the constant cross section A2. P1 and P2 are the pressures in the region 1 and the region 2 that we are studying. Okay, so let's see what is work done on the fluid at this end BC. Call it W1. This will be equal to pressure into the total volume. Volume is A1, the area of cross section, multiplied by the length V1 delta t, and so I can write this as P1 into delta V. Easy. The work done at the other end W2 is P2A2 V2 delta t, which is equal to P2 delta V. So the work done in the fluid in that region, the second region, is equal to minus P2 delta V, and the total work done therefore becomes equal to W1 minus W2 is equal to P1 minus P2 into delta V. So the total work done in the fluid W1 minus W2 is equal to P1 minus P2 into delta V. Okay. Now this work done, P1 minus P2 into delta V, it does two things. It changes the kinetic energy of the fluid, and it also changes the potential energy of the fluid. Okay, so two changes occur because of the work done. Now, if we consider the density of the fluid to be rho, because the liquid is incompressible, it will remain the same at all points during the flow. So delta M, which is the mass delivered at say at the first cross section, that will be A1 into V1 delta t multiplied by rho. Now, I can write for the delta potential energy, change in potential energy, as a symbol delta U, and this delta U turns out to be equal to rho G delta V. Okay, H2 minus H1. rho g delta v. Rho delta v gives the mass into the acceleration due to gravity. So this is the gravitational potential energy which is changing, and the second height is h2 minus h1, the first height. So the change is equal to this rho g delta v, h2 minus h1. And the change in the kinetic energy, which I write as delta k. Okay? This is the symbol that normally we use. This is equal to half mv square. Okay? One minus the other. So it is half rho delta v, which is the mass, v2 square minus v1 square, the velocity at the other end minus the velocity at this end. So the work energy theorem that I talked to you about for the conservation of mechanical energy, okay, this will give us the work done P1 minus P2 delta V is equal to half rho delta V, V2 square minus V1 square plus rho G delta V H2 minus H1. Okay. So this delta V here, and delta V here, and delta V here, they cancel out. And I get the relation P1 minus P2 is equal to half rho V2 square minus V1 square and rho G H2 minus H1. Okay. So this is the equation which we get in the Bernoulli's principle, and this we are going to write otherwise to show you the beauty of the Bernoulli's principle. Okay. So we can take up that equation P1 minus P2 is equal to half rho V2 square minus V1 square, which is delta kinetic energy per unit volume, and rho G H2 minus H1, which is the delta potential energy per unit volume. If I separate the terms at the level 1 and the level 2 respectively, and what I find that P1 plus half rho V1 square plus rho GH is equal to P2 plus half rho V2 square plus rho GH2, and therefore I am tempted to write in general that P the pressure plus half rho V square, which is kinetic energy per unit volume, and rho GH, which is the potential energy of by virtue of its gravitational position, potential energy per unit volume. And this turns out to be, because 1, 2, 3, 4, everything is constant if we take so many points. So in general we take it, and this is the equation which is describing the Bernoulli's principle. There are two things in the Bernoulli's principle. One is that in deriving the Bernoulli's principle, we have considered that the fluid is incompressible. The second thing is that our consideration has been only 3 items: the energy due to pressure, energy due to motion, and energy due to position. These are the 2 mechanical energies, and therefore in the process of the flow that takes place over here, we consider that no energy is lost due to friction. There is no friction, no energy is lost. This is what we consider in the derivation of this thing. However, that's not true. In the motion of fluids, there are frictional forces which are provided by viscosity. So there is a loss in energy, which can, if there is a loss, that can be in the kinetic energy, maybe because H is a constant, P is there. So this is the loss of the energy is in terms of heat energy. Okay. So we can write, now from this equation I can write, if I take out this term, okay, half rho v square, for a fluid at rest, the velocity is equal to 0. So I am left with rho g h plus p is equal to a constant, which says that p1 minus p2 is equal to rho g h2 minus h1. Okay, so in that special circumstance, when the fluid is not made to move, it is at rest, then it so happens. Next, we'll talk about Torricelli's law, which gives the velocity of efflux. Also Venturi meter, blood flow and heart attack, and some other things before we take up viscosity. So be there. I would like to, am longing to have questions from you, pouring in from you, okay, which the rate of the questions that you ask has been not very, and of course constructive criticism, even destructive criticism, I don't mind, but of course don't start calling names. That's not a proper thing to do for young people like you. Okay, so I take your leave, meet you sooner with Torricelli's law, Venturi meter, blood flow, and of course heart attack. Bye for then.